I will begin with a word of prayer. Ahem.
We are praying.
Yes, thank you. Heavenly Father, we thank you for this day. I thank you for these students. Pray that you'd help us to just understand more about your creation today, just to understand how to solve differential equations with linear algebra. Just pray that you'd give understanding to the students today, Lord. In your name I pray. Amen. All right, so I guess first things first, I probably should give you an example of what is a system of differential equations. So let me just give you an example to start us. If you have dx dt, which I'm going to say is x prime, just for the sake of not writing dx dt a bunch of times. And then you have y prime, and then you have z prime. And let's suppose that those are equal to, I don't know, x plus y plus z, x minus y, and x plus 2y minus z. This would be a system, in fact, of a homogeneous system of ordinary differential equations. Now, you can rewrite this in the following form. You can rewrite it as the derivative of this vector, x, y, z, is equal to this constant matrix, 1, 1, 1, 1, minus 1, 0, and 1, 2, minus 1, multiplying by x, y, z. And so this is a homogeneous system. Now, here's our typical notation. We'll instead write this like this, dx dt. I'll tell you what, let me use, well, I usually do use x vector. You shouldn't conflate that, confuse it with the x here. They're different, right? If this is a problem, you could write dr dt or something. But anyway, this is equal to a times x. So this is the coefficient matrix for this linear system. And here x is a variable of here x is not like the x we thought about before. It's, it's a particular vector in Rn we're looking for or something, right? But you notice that now this x is actually a vector of functions of time. So that's the kind of solution we're looking for now, not just a tuple, but a tuple of functions. So the question then is, well, how do you solve things like this, right? So that's a question we can ask. Now, more generically, guys, you could have something like this. If you have, say, dx1 dt is equal to a1, 1, x1, plus dot, 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 plus a1, n, xn, plus f1, and repeat this story until you get to the nth variable, dxn dt is equal to a n1, x1, plus dot, 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 plus a n, n, xn, plus fn. You could rewrite this system of n differential equations and n unknowns. You can rewrite it as dx dt is equal to ax plus f. If f is not equal to 0, then it's the so-called inhomogeneous differential equation. I don't think I'm going to talk much about the inhomogeneous case today at all. I'm mostly just going to talk to you about how to solve the homogeneous problem. All right? And I'm being rather boring. I'm supposing that we have n differential equations and n unknowns. I'm not thinking about an overdetermined or an underdetermined case. You could think about those things, but we won't. All right? How do you solve this problem? That's the question. Well, there's a theorem. The theorem states the following. It says the system dx, and I'll give a specialized theorem, but the theorem is basically this: dx dt equals to ax has a general solution of the form x is equal to c1x1 plus c2x2 plus dot 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 plus cn xn, where these x1, x2, dot 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 xn are linearly independent solutions to star. We'll call this thing star. So now I can't prove this theorem in here. No. What I'm saying is any solution can be, if you can find n linearly independent solutions to the homogeneous problem, any possible solution to this problem can be formed by a linear combination of these n fundamental solutions. The proof of this lies outside this course. This is a problem of analysis, but that is a theorem that is known, the so-called existence and uniqueness theorem. Now, okay, so the thing to do here is not to think about column vectors, though. What we want to do to come to a more efficient understanding of how to solve these things, a better way to look at this is that this is really, let me do it in a different color. This is a better way to look at this, perhaps, is that this is really just x times a constant vector, where this x is the fundamental solution matrix. What's a fundamental solution matrix? Well, a fundamental solution matrix is simply formed from concatenating the fundamental solution set, gluing the n solutions of time together to make one grand glorious n by n matrix of functions of time. So this is like x1, x2, xn. Yeah, these are, every component is in fact a function of time in this context. Now, so that's in the notation of the theorem, that's what it is. What makes something a fundamental solution matrix is two things, right? So if you calculate dx dt, what do you get? How do you differentiate? In fact, if you differentiate component-wise. That's the definition. So like if that's dx1 dt, dx2 dt, and so forth and so on. All right? Like so. Now, if each one of those is a solution, what's that look like? We can replace, if each one of these is a solution, that means that they're equal to what? A times x1, a times x2, a times xn, right? But what can we do then? What do we know about matrix multiplication? We have the concatenation proposition, right? We can peel that a out, and we can rewrite this as a times x1 concatenated all the way down to xn, right? In other words, a times x. So a fundamental solution matrix, a matrix which is comprised of the concatenation of column vector solutions, is necessarily a solution to a corresponding matrix equation. You see, we have dx dt is equal to a times x. This single matrix equation contains within it n column equations, right? That's a very efficient notation, right? And what's the other thing? For it to be a fundamental solution matrix, the other thing is more linear algebraic, let's say. It's that the columns have to be linearly independent in the sense of functions, all right? So technically, the linear independence I'm talking about is like c1 x1 of t plus dot 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 plus cn xn of t equals to 0 for all t in the domain. In this case, the domain is just all reals. That has to imply c1 equals 0, cn equals 0. This is the linear independence of functions of time. It's a functional equation. It's made for all time, not just, All right. Excuse me. Okay, so that's a fundamental solution matrix. Now, I want to show you something about the matrix exponential we looked at last time. Recall? E to the AT is what? It was by definition I plus TA plus 1/2 t squared a squared plus 1 over 3 factorial t cubed a cubed. I'll go one more just to make a point. 1 over 4 factorial t to the fourth a to the fourth, and so forth. That's the matrix exponential. If you work out the analysis of this, differentiation term by term of a series of matrices makes sense, just like differentiation term by term of a series in Calculus 2 makes sense, for much the same reasons, in fact. So if we differentiate this, what do we get? d dt of e to the at is equal to what? Work it out. Try it out, guys. Differentiate ta, what does that give you? That gives you a. So basically a is a constant here, right? A is a constant matrix. It just rides along. Differentiation can't hurt it. Well, actually it could make it 0. But so it better be attached to a t, otherwise it's dead. Like the identity matrix differentiates to 0. Gone. But this gives me an a. This gives me plus t a squared. This guy gives me plus 1/2 t squared a cubed. This one gives me a 4 over, what's 4 over 4 factorial? 4 over 4 factorial is 1 over 3 factorial, t cubed a to the fourth, and so forth. Now if you tilt your head and squint, you can see that we should factor out an a here, right? Factor out an a, that gives us I plus ta plus 1/2 t squared a squared plus 1 over 3 factorial t cubed a cubed. Was that of understanding? What's that?
It's very pretty, because then the a just ends up in front of it.
Yes, yes. And you could put it on either side, right? I could have factored the a out this way or that way.
It belongs in front.
It belongs in front, okay. I'll accept it. This is e to the a times e to the ta, yeah? What was the question? What is it?
No, I was wrong.
Oh, okay. What's the significance of this calculation? Last time we argued that e to the ta inverse is equal to e to the minus ta. Okay, I didn't have a t there at the time, I just had an a. Multiply by t, it's still true. So, it's an invertible matrix. That means it has linearly independent columns, right, for each time. It follows that this condition holds true for the columns. So it's a linearly independent with columns, and it also solves, it's, e to the at. If you think about it this way, x equals to e to the ta solves dx dt equals to ax. The matrix exponential is a fundamental solution matrix to the problem dx dt equals to ax. So we're done. We solved it. Right? I told you that this is the general solution, right? I just told you basically, just here it is. Here it is, x prime equals to ax. Actually, dx dt equals to ax. Thus, x equals to e to the ta times a constant vector is solution. It's the general solution. Done. That's true, but is that a good general solution? Good in the sense of, can you compute it? Think about what the matrix exponential is, right? It's this unending series of powers of matrices, right? It's kind of, it's a mixed blessing. We have a solution matrix. If we could calculate the matrix exponential, every column in the matrix exponential would separately be a solution to the system. But how do you actually do that, right? That's where the magic formula comes into play. The magic formula. which I call the magic formula because it's magical. Simply speaking, e to the ta is equal to e to the t lambda times, oh fine, I'll derive it. So this is e to the t times a minus lambda I plus lambda I just added 0, which by the way is e to the t times a minus lambda I times e to the lambda it. I can do that because a scalar multiple of the identity commutes with any matrix. So by the laws of exponents I mentioned to you guys last time, I can split it up into a product of the exponentials. Now that's an exponential of a diagonal matrix. So that is in fact just equal to e to the lambda t times I. I'm just going to put that out front. So I'm just moving that over to here. That's using the exponential of a diagonal being the diagonal of the exponentials. But in this case, it's got the same number down the whole diagonal. So it's just one exponential, and I can factor it out. And that's where the magic happens. That is the identity plus t times a minus lambda I plus 1/2 t squared a minus lambda I squared plus 1/3 factorial t cubed a minus lambda I cubed plus dot 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 dot. So let me erase the I here because it's obnoxious. Here's my proper magic formula, e to the lambda t. So there you go, there it is. That's the magic formula. This, if we write the matrix exponential in this format, it's exceptionally useful. You could say, well, what's lambda? It's true for any lambda. The calculation I did doesn't specify any particular necessity on lambda. I mean, lambda could be anything. If you search your heart and you check out the details, lambda could be complex. This would still make sense. In fact, well, if lambda is complex, I think I've gone to the complexification of the exponential, technically speaking, to be fair. And there it is. Now, who cares? What does this help you? Well, check this out. So, for example, if I want to solve dx dt equals to ax, where let's say a times v1 is equal to 3v1, and a times v2 is equal to minus v2, right? Suppose it's a 2-by-2 problem. I need to find 2 linearly independent solutions, magic formula, and the exponent, and these eigenvectors. All I need. See, if I look at e to the ta times v1, what do I get? And what we do is we put lambda equals to 3 in the magic formula, right? So this gives me e to the 3t, and I'll write it out a few times. Once you understand the magic formula, you don't have to write it down. You can just use it. I only write that much because I don't need to write more. So when you multiply this vector on this infinite series of matrices, what do you get? You're like, a headache. Hey, don't laugh. You said that. That's ridiculous. This is the most interesting and exciting math I've seen in some time. Can we stay overtime today? This is so very exciting. Yes, I heard your request. I will do it for you. But, and so forth. Like, the terms beyond this have like a minus 3i squared, cubed, 4th power, and so forth and so on. But what's the deal with a minus 3i times v1? That is 0 because v1 is an eigenvector with eigenvalue 3. This is 0. And so is everything else. So this just gives us e to the 3t times v1. I could sometimes call this an eigensolution, because it's one that's derived simply from an eigenvector. Likewise, x2 will be equal to e to the ta times v2, which would be e to the 2t. I'll use the magic formula with lambda equals to 2, because that's what suits my purposes here. Now, did I really need to write all that down? Not really. I mean, if you understand what's going on here, you would just write down e to the 2t times v2 as the solution, the second eigensolution. Then I go back to the existence and uniqueness theorem, which tells me, hey, once you find linearly independent solutions, you put them together, make a linear combination, that gives you the general solution, which is usually what we're after. So you put this together, therefore the general solution, x of t, is equal to c1 e to the 3t v1 plus c2 e to the 2t. Oh, why do I have 2? E to the 2t, v2 there. Phew, almost. That is one of the rights and privileges that is guaranteed unto you once you get a PhD in math. You're allowed to do that. I'm not technically allowed to do that in physics because I only have a master's. I'm not allowed to modify problems midstream. But there you go. I mean, that makes sense? No? Well, sorry. Don't. Let me look at another example with you guys. What if we had a matrix? Another example here. What if I had let's say a 4 by 4 matrix with A times V1 equal to, let me make it more simple. Let me say it's A minus 3i times V1 is equal to V2, and A minus 3i times V2 is equal to 0. And let's also suppose that A minus I times V3 is equal to 0, and A minus I times V4 is equal to 0. And I'm assuming that V1, V2, V3, and V4 are themselves linearly independent vectors. That's important. As a set, these are linearly independent. Okay, so listen, there's some low-hanging fruit here, right? By the same argument we just went through, can you guys tell me immediately 3 solutions? Let's call them eigensolutions for the sake of. How about x? Let's say x2, right? Would be e to the at times v2. Essentially, there's a theorem that if you take an eigenvector and you multiply it by the matrix exponential, what pops out is e to the eigenvalue of t times the vector again. That's all that happens, right? This is actually equal to e to the, what was the eigenvalue for v2? 3, right? So this is e to the 3t times v2. By the same calculation I did over there, with lambda equals to 3. And also, what else do we get? x3, using the same numbering, I've got e to the at times, how do I know that e to the exponential times a vector gives me another solution? There I'm using something I haven't proved for you, which is that this is a linear differential equation, a homogeneous linear differential equation. One of the fundamental things about it is the sum of solutions is again a solution. Well, if I take a matrix exponential times a column vector, what is that? That's a weighted sum of the columns of the matrix exponential. Each column being separately a solution, a linear combination of said solutions is once more a solution. So it is in fact the case that this has to be a solution to the differential equation. I think I might have slipped that past you. That might have been what Mr. Anderson was confused about over here. Why was it a solution? I don't know. Maybe that could have been part of it. But the reason that this is a solution is it's a linear combination of columns of the matrix exponential. And we just proved over here that every column is a solution. Anyway, this here then is what? This is e to the t, right? Eigenvalue 1. I see that from here, v3. And x4, e to the at times v4, e to the t times v4. For those of you who are taking differential equations right now, I want you to notice something about this. No multiplication by t, even though we've got lambda equals to 1 twice. I'll get back to that comment after this example. And what do we do with this up here, though? Yeah.
Just to go back to where you said there's no multiplication by t,
Mm-hmm.
Is there any way where you can like in differentials when you have t or t squared in front, you can kind of, you know which which constant is associated with which form? Is there any way to do that with this, where you can kind of backtrack where each of them is like a particular thing, like that is?
Yeah, if you were to tell me this is the general solution to x prime equals to ax, I could look at the general solution and tell you the Jordan form of the matrix. Yeah. Conversely, if I have the Jordan form, I can write down the general solution. That's what I'm working through, example by example. But yeah, that is true. Now, so this one, what I got to do is I got to take e to the at. I'm going to call that x1 why not, right? E to the at times v2. That's the one I have, v1 rather. So this would be e to the 3t, magic formula, right? The identity plus t times a minus 3i plus 1/2 t squared a minus 3i squared plus dot 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 multiplied by v1, right? Now, of course, we could save ourselves some writing and just multiply the v1 through to start with, right? Like, just multiply v1 in here. What do you have? You got v1. This multiplies by v1, right? This multiplies by v1, right? Now, so I've got e to the 3t times v1. And then what's this equal to? v2, right? By assumption. I mean, that was data that we were given, because I've arranged them in Jordan chains. Besides just being cool linear algebra, the existence and structure of Jordan chains naturally couples with the structure of the magic formula to give you just pretty solutions. Here it is. What happens here? We get a minus 3i. The first thing pulls down a v2, right? But what is a minus 3i times v2? Well, that's 0, right? Because v2 is an eigenvector. v1 is a generalized eigenvector of order 2, which of course is why this has gone to 0, right? Because v1 being a generalized eigenvector of order 2, this is 0. And there you go. That's the solution. x1 is equal to e to the 3t times v1 plus t v2. Now, what's the that's just the fourth solution. To actually find the general solution, what do I have to do? X is equal to c1 x1, right? c1 x1 plus c2 x2 plus c3 x3 plus C4, X4, where they're as I found them. That would be the general solution. I just don't want to write it again if you don't mind. All right? It's comprised of 3 eigensolutions, and I would call this a generalized eigensolution, right? You see my language? I don't know how general this, I don't know how common this language is, but it makes me happy. I don't know. All right, now what I want to do now is shift gears considerably. You can say, well, but you're just solving a very special kind of linear differential equation, right? You can go on with this story, right? If you understand these examples I did, you see that if we have a matrix, if we find a Jordan basis, we just feed the Jordan basis in chains to the magic formula, and it will spit out stuff like this. I have many more examples in the notes for you to look at. I'm not going to do more here right now. I want to get to the bigger picture. So you might wonder, though, right? Oh, why am I using that? Ugh, that's what I should wonder. You might wonder, so you're just solving x prime equals to ax. How do you know that that's really general? I mean, aren't you making a very special assumption when you assume the differential equation has that form, right? And the answer happens to be no. Like, any linear differential equation can be recast as a system of linear differential equations in normal form. The normal form is what I had over there before I erased it in green. I want to show you how that plays out for 2 specific examples that if you've had 334, you've dealt with. All right? Example 1, how about this? Y prime prime minus 2y prime. I better do a third order, otherwise it's too boring. Y prime 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 plus 3y prime prime plus 3y prime plus y equals to 0. What you learn in differential equations is you write down the auxiliary equation, or we also call it the characteristic equation, lambda cubed plus 3 lambda squared plus 3 lambda plus 1 equals to 0. All right? You factor that. This happens to be lambda plus 1 cubed equals to 0. And then the theory you go over in Math 334 tells you to write down the following solution. Y is equal to c1 e to the minus x. Let me use a t here. c1 e to the minus t plus c2 t e to the minus t plus what? c3 t squared e to the, yeah. So you guys know that, right? I mean, you're like, I missed those examples. Those were nice. That was a happy time. It's an unhappy time now, right? Are you doing series? Yes, series. It's more fun. Unfun. But you're not doing the Frobenius method, right? Are you doing the Frobenius method? Oh, Frobenius method. Anyway. Okay, so that's a linear differential equation. Third order linear differential equation. How do you rewrite this as a system of first order differential equations? Well, there's a standard technique. What you do is you say x1 is equal to y. You say x2 is equal to y prime. You say x3 is equal to y prime prime. And then that does it. So x1, so check it out. x1 prime is equal to what? Y prime, which is equal to what? By definition here, x2, right? So I'm showing you a technique which is called reduction of order. So it turns out you can use reduction of order to convert any higher order differential equation to a system of first order differential equations where the sort of net order is preserved. x2 prime is what? Well, that's y prime prime, which is what? x3, all right. And x3 prime looks like a y prime prime prime, which is what? Well, then you got to go back to the differential equation. See what it is? It's this minus 3y prime prime minus 3y prime minus y. If you've studied chapter 7, you should be starting to have this like nagging sense of deja vu here. Let me make it more explicit. If you rewrite this as a matrix, you've got x1, x2, x3 prime equals to what? 0, 1, 0, 0, 0, 1, and, oh, sorry, one more step. What was this equal to? Negative 3x3 minus 3x2 minus x1. So you got a other order, but it's minus 1, minus 3, minus 3. That's almost a companion matrix for us, right? If you transpose this matrix, you'd have a companion matrix, right? So if the transpose of this is a companion matrix, I think we can, without calculation, tell what the characteristic polynomial is for this thing. What's the characteristic polynomial for this? If this is A. The characteristic polynomial of A as a function of lambda, let's say, is going to be lambda cubed plus 3 lambda squared plus 3 lambda plus 1. You could work it out, but that is what it is. That's the determinant of lambda I minus A. It's the same as this one. It's not an accident. That fundamental structure is still there. Okay, so great. That means that this has what? Lambda plus 1 cubed, right? So what are the eigenvalues for this matrix A? Minus 1. With multiplicity, algebraic multiplicity, 3. All right, so let's find them. So let's see here. A plus I is what? Fun. 1, 1, 0. Oh no. 0, 1, 1. Minus 1. Oh man, minus 3. I might actually have to calculate something. Minus 2. Gah. I need a vector that when I multiply on this, I get 0. What should I use for my eigenvector? Can somebody just guess it for me? What vector, when I multiply on that matrix, gives me 0? It can't be 0. Zero's, you guys. 0 is not an eigenvector. Killing me. What's that?
Yeah, like zeros everywhere except where there's zeros in the first one.
Can you tell me the vector?
Like the column.
Negative 1, 1, 1? Negative 1. How about let's put the minus in the middle. Let's try that out. 0, 0. Please, 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 please. Minus 1, plus 3, minus 2. Woohoo, we have a winner.
Hey.
All right. Now, of course, you could do row reduction. Yes, thank you. What is that? Is that, did you Fonzie the calculation? What was that? I don't know. Is Fonzieing a verb? I don't know. So then what you want to do is you want to solve A plus I on V2 equals to V1. Okay, that's the next game you play. So the question is, I want to look at 1, 1, 0, 0, 1, 1, minus 1, minus 3, minus 2. And I'm trying to get it equal to 1, minus 1, 1. Probably I've got to start doing row reductions. Let me do a row reduction. I'll be a good citizen of the mathematical world here. No more guessing. Not yet, anyway. So add row 1 to row 3. We get 0. We get minus 2. We get minus 2. We get... I'll get out of the way here in just a second. Yeah, I have yet to find the active camouflage that I need to make my lecture more accessible. You can't see through me yet. I mean, sometimes you can, but not on tests, apparently. I don't know. I wish. So these two are the same. right? So ignore one of them. And all right, so I see what's going to happen. I can do what? I basically have to solve u plus v equals to 1 and v plus w equals to minus 1. Why don't we just set v equals to 0 for our convenience? And if we set v equals to 0, we'll get u is equal to 1, w is equal to minus 1. Bam, we're done. v2 is equal to, what do you get? What did I just say? 1, 0, minus 1. There's my generalized eigenvector of order 2. I'm solving the chain going up. As I warned you, this is a dangerous thing to do. But it's only dangerous when there are multiple chains. There's just one chain here, so we probably are not going to get into trouble. And then you got to find the third one, which would be to solve what? Next, we're going to solve a plus I v3 equals to what? Equals to v2. Can you guys solve that for me real quick here? We were looking at 1, 1, 0, 1, 0, minus 1, 0, 1, 1, minus 1, minus 3, minus 2. Okay, basically the same row reduction, I believe. So we get 1, 1, 0, 1. We get 0, 1, 1, 0. Adding these two gives us 0, minus 2, minus 2, 0. Right? So the equations which govern v3, you can see them from, I don't need to do further row reductions. I can see it from here. I've got u plus v equals to 1, and I've got v plus w equals to 0. It looks like I can still get away with choosing v equals to 0, right? If I set v equals to 0, that says what? U equals to 1, and w is equal to 0. I have to be careful. I can't make a choice which gives me the 0 vector. That would not be allowed. And so anyway, long story short, we have v3, which is 1, 0, 0. All right, now, what do I do? Let's write down the general solution using the magic formula, which I just erased. Sorry. So x of t is equal to c1 e to the minus t v1, because v1 is an eigenvector, right? So it gives us the solution, plus c2 e to the minus t times v1 plus t v2, because v2 is a generalized eigenvector of order 2. So the calculation I did over there happens again. What happens if you keep one more term? Plus c3 e to the minus t v1 plus, I'm sorry. No, that's not, this is what I get for skipping steps. What should happen here? I'm trying to calculate what is e to the at times v2. E to the minus t times what? Times v2 plus t times a minus I, or plus I should say, v2, right? This works out to e to the minus t times v2 plus t v1. The eigenvector goes with the t1. I've got them flipped here. Let me be careful. If we're careful, we work it out. We have the 2 up here minding its own business and the eigenvector over here. When you get to the third one, you get 3, 2, and then 1/2 t squared times v1. That's the general vector solution to this system of differential equations we found. Now, what do we actually care about here? If you think about it, what's its origin story? Right here, this y prime prime plus 3y prime plus 3y prime prime plus 3y prime plus y. So to find the solution to the original differential equation, what should I look at? To understand the solution of this from my eigenvector magic formula junk over here, what do I need to look at? I just need to look at the top component, right? The first component is the x1, which is y. So focus on the first component. What does that give us? You guys have to follow along here. We have x1 is equal to y. c1 e to the minus t. What's the top component in v1? It's 1, right? So that's a 1. Plus c2 e to the minus t. Now you guys tell me, what do I put here? What's the top component in v2? 1, all right. And then what? I have t times the top component in v1. What was v1? Oh, 1 plus t, right? And then plus c3 e to the minus t. The top component in v3 was what? It was 1. The top component in v2 was what? Oh, they're all 1, aren't they? Sorry. That's a quirk of this example, that they're all 1. And for those of you who have studied differential equations, you should realize that this is just a quirky way of writing your usual solution, right? You can redefine, say, c1 tilde e to the minus t plus t c2 tilde e to the minus t plus c3 tilde t squared e to the minus t, right? And that would be the same general solution. So what I'm trying to show you guys is that the appearance of the t and the t squared in the third order repeated case is actually explainable in terms of the Jordan form and the existence of generalized eigenvectors of order 2 to get the t, or generalized eigenvectors of order 3 to obtain the t squared. Right? Let me work this backwards. Now, this won't make sense to you who have not had differential equations. I promise that. I can assure you this won't make sense. I mean, it might. I don't know. You guys are pretty smart. You might figure it out. You doubt it? Have some more faith in yourself. Come on. Let's see here. God's creation. Don't rule things out. Let's see here. So check this out. If I look at the differential equation, check this out. So suppose I had d squared plus 4d plus 5 as a differential operator acting squared, acting on y equals to 0. If you were to multiply this out, this would give you something like y prime 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 prime. Help me multiply this out, guys. Plus what? When you square this, what do you get? I'm just going to do it. What does that give you? How many? We get d to the fourth. How many d cubes? 8. Okay. How many d squareds? 26. All right. How many d's? And how many just plain 25? This differential equation, if you've done your due diligence, if you've covered the requisite cases in Chapter 6, I don't know what book you guys are using. It's in Chapter 6 of Nagel, Saff, and Snyder. What you find out is that the solution has the following form. Y is equal to C1. This is d plus 2 squared plus 1. Yeah? Completing the square. So what you got is you got yourself an e to the minus 2t cosine of t plus c2 e to the minus 2t sine of t plus c3t e to the minus 2t cosine t plus c4 t e to the minus 2t sine t. Check this out. If we do reduction of order, x1 is equal to y, x2 is equal to y prime, and so forth, what do we get to? x3 is equal to what? Oh, duh, y prime prime. x4 is equal to what? Y prime prime prime. So what do you got? You got yourself x1, x2, x3, x4. What's the companion? What's the matrix here? It's 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And then the last one is what? Minus 25, minus 40, minus 26, and minus 8. Where do these cosines and t's come from?
Is it because the solutions are in the imaginary number?
Mm-hmm. They have the same characteristic equation. This invariance, the fact that you have this characteristic equation here and the same characteristic equation for the companion matrix, which is the system of the reduced system, it's the same for this, same for anyone that you do this reduction of order. So this has a characteristic polynomial which has complex eigenvalue minus 2 plus or minus I repeated. And I can tell you from my experience on that one that the existence of these t's in the solution means that this 4x4 matrix has complex eigenvalue minus 2 plus or minus I with geometric multiplicity 1 and algebraic multiplicity 2. In other words, there exists a generalized eigenvector with complex eigenvalue minus 2 plus I. I can see that from the fact that I have them over here. But you can do the other way around. You can also find the real Jordan form and feed it to the matrix exponential, select the real and imaginary components, and that will give you the solution in the case of complex eigenvectors. I have many details in the notes. I'm sorry I couldn't work it in today. Fine. I'll stop. Thank you for your homework. I will post the solution to Mission 7 because my intention to this was not just to be mean. It was to give you something to work with for quiz 2. I think you now understand what you don't understand, yeah?
More or less.
More or less? Yeah. Yeah.